Hello students, hope you guys are doing well. I would like to start this first video by recalling that what we were doing towards the end of the last lecture. If you remember, we learned how to calculate the basis for four fundamental subspaces associated with matrix A of size m by n. We also noticed that the basis for the row space is orthogonal to the basis of null space of matrix A, and the basis of the column space, they were orthogonal to the basis for the left null space. Well, this was just an observation, and if you remember, towards the end of the last lecture I gave you a set of four definitions that were about orthogonality, right? Let's recall those four definitions. I don't really want to rewrite all four definitions again, but I just wanted to show you how we have worked, how we got a very interesting definition from this set of four definitions. The first definition was a definition of orthogonal vectors. Remember, two vectors are orthogonal if their dot product is 0. Alright, so u and v are orthogonal if their dot product is 0. So this is the standard definition of orthogonality of two vectors, right? Using this, we define vector orthogonal to a set. Suppose I give you one vector u and I give you a set of vector, let's say v1, v2, vn. We can say u is orthogonal to S if dot product of u with every single element, every single vector of set S to be 0. Alright, so in other words, u dot vi to be 0 for I running from 1 to n. Alright, we also define orthogonal sets, two orthogonal sets, right? So, or let's call them orthogonal subspaces. We were talking all these things in terms of vector spaces. So let's say you have a vector space V, and inside a vector space you have a small subspace. That subspace is orthogonal to vector u if your vector is orthogonal to every single vector sitting in that subspace. Two vectors in vector space are orthogonal if their dot product is 0. Two subspace are orthogonal if every vector in the first subspace is orthogonal to every vector in the second subspace. So suppose I give you two subspaces u and w of vector spaces. These two subspaces are orthogonal if every vector here is orthogonal to every vector in U. Alright, so that's also something that we have defined in the last lecture. I also define a very interesting concept. We call it orthogonal complement. Remember, let me write down that definition. Let W be a subspace of a vector space V. Alright, so you have a vector space V that satisfies those 10 amazing properties, and you have some subspace W of vector space V that itself is a small vector space inside that big vector space under the same operations. Alright. So suppose W is a subspace of a vector space V, then the set of all vectors perpendicular or orthogonal to W is called an orthogonal complement of W. Mathematical notation of orthogonal complement is fairly simple. You write W and in the power you put that upside down T. We read it as orthogonal complement of W or W perp. Alright, so perp or perpendicular, W perpendicular or W perp. Okay. Okay, so remember I gave you example of orthogonal vector to the set, two orthogonal subspaces, and now let's talk about few simple example of orthogonal complement. Here is one illustration. Let's say I give you these two sets, W equal to xy plane in R3. R3 is a vector space under usual addition and multiplication by scalar perform over order triple, right? Its orthogonal complement contains set of all those vectors that are perpendicular to xy plane. Remember, set of all vectors perpendicular to xy plane, they are the vectors parallel to the z-axis, right? So z-axis is going to be orthogonal complement of this subspace W. Now think about it for the second. What orthogonal complement really does? Orthogonal complement, it's a very nice way to divide the entire vector space into two perfect pieces. Alright. If you glue them together, you get the whole vector space V. In other words, every element of your vector space V can be expressed as a linear combination of vectors from W and its orthogonal complement. And this is the reason, this is a very nice way to split, the entire vector space into two pieces that are orthogonal to each other. Think about it in terms of R2. Remember, this plane R2, x-axis and y-axis, these are two subspaces of R2, right? X-axis, any line through origin is a subspace of R2. Y-axis, it's also subspace of R2. And as you see, using x-axis and y-axis, vectors on x-axis and y-axis, you can express any vector in R2. So that's the beauty of subspace and its orthogonal complement. They both together forms the entire vector space. Alright, so they are like perfect partition of your vector space, and that's why we are interested in this very interesting idea. I'll tell you very quickly, very shortly, what is the connection of this whole thing with the remark that we have seen in the last lecture. Alright, okay, so before I move further, let me give you some remarks about orthogonal complements. Okay, so here are few interesting remarks. Remark number 1. Orthogonal complement of W is a subspace of a vector space V. Alright. Again, we have seen many examples and we have proved that given set is a subspace of a vector space or not. What I want you guys to do is check if orthogonal complement is a subspace of vector space or not. Let me give you the definition of orthogonal complement here in terms of set notation. Look, W perp contains set of all those vectors U for which U dot V is 0 for V being in subspace W. Alright, these are set of all those vectors whose dot product with every vector in W to be 0. Alright, so show that this is a subspace of V. You need to show those two conditions. Closure property under vector addition and closure property under multiplication by scalar. Okay, I'll let you guys prove that. Okay, remark number 2. In W and its orthogonal complement, the only common element is the 0 vector. And it's very clear that, look at this example, x-axis and y-axis, the only common vector or the only common element between these two pieces is really the 0 vector. Alright, 0 vector is the only vector that is orthogonal to everything in W and everything in W perp. Alright, so be sure that you know that this is kind of obvious thing. We can prove it using left side and right side, right? So take any element in here and show that that element has to be 0. Alright, other way around is trivial, that 0 is already part of both of them. Alright, okay, remark number 3. If you compute orthogonal complement of orthogonal complement, then you get back W. Alright, so simply orthogonal complement of x-axis is y-axis and orthogonal complement of y-axis is going to be x-axis. So x-axis orthogonal complement of orthogonal complement needs to be same as x-axis. Alright, quite trivial thing. Remark number 4 is slightly more interesting. So let's write down remark number 4. It goes like this: if U is orthogonal to vectors v1, v2, vn, then U is orthogonal to any linear combination of v1, v2, vn. So k1 v1 plus k2 v2, so on, kn vn. Alright, a very crucial remark. If vector is orthogonal to a set of vectors, then the same vector will be orthogonal to any linear combination of v1, v2, vn. Alright, why do we need this? Because we would like to make some comment about orthogonality of those 4 fundamental subspaces. Alright, my intention is very clear that, remember, to represent a subspace you don't have to write down all infinitely many vectors. You just have to write down their bases. Bases are the vectors, set of vectors, finite vectors, that gives you an opportunity to represent all infinite entry within that subspace. Alright, and this is the reason why we are interested in that definition, that U is orthogonal to v1, v2, vn, then it's orthogonal to its linear combination 2. Meaning, to show that two subspaces are orthogonal to each other, all you have to do is show that their bases are orthogonal to each other, and that's pretty much it. It's as simple as that. This is the reason why we have constructed this step-by-step set of definition to introduce this perfect piece coming from a vector space V, which is orthogonal to the given subspace. Alright, now with this whole information, I would like to give you one very clear example of what this four fundamental subspaces does. Alright, so remember that we know that row space of A was orthogonal to the null space of A, and column space of A was orthogonal to the left null space of A. This is something that we know already from the last lecture's observation, right? As I mentioned that this is how row space and null space are connected. A row space of A so this is row space of A. We know that dimension of row space, dimension of column space, they are the same, and we call it the rank of A. Suppose these two dimensions are, let's say, R. Alright, row space of A and null space of A, we are saying that they are orthogonal complement of each other. So these two pieces, they are perfect partition of Rn, meaning any vector in Rn can be expressed as a linear combination of bases coming from the row space and bases coming from the null space. Alright, likewise any columns of A column space of A and left null space of A these are two subspaces of Rm. Alright, so these are perfect partition of Rm. Any vector in Rm can be expressed as a linear combination of bases from Ca and bases from null space of A transpose or left null space. Okay, now let me show you what do we mean by solving system Ax equal to B. Okay, this is again a very crucial thing, because from the beginning of the course we have been talking about solving system of linear equation of the form Ax equal to B. What do we really mean by that in terms of those nice pieces? Let's try to understand that. Okay, so I'm going to draw the same picture down here, which will give you a brief idea about how these four subspaces are related to each other. So I have this first subspace that I call a row space of A, Ra, and we know its dimension of Ra, let's say it's R. Okay, the subspace that is orthogonal to this, null space of A, dimension of null space of A is going to be n minus R. Okay, alright, what's common between subspace and its orthogonal complement is the zero vector only, and this is really orthogonal. Alright, it's orthogonal. Zero vector is the only common element, common vector between them. Okay, alright. And here are two subspaces of Rm. I have a column space of A with dimension same as the row space. You have the same number of basis entries in row space and column space for the obvious reason that those echelon form contains the same number of pivots. Alright, so this is left null space. With dimension is m minus r. Dimension of this is n minus r, dimension of left null space is m minus r. So this is m minus r. Okay, alright. So when we solve the system, this is how we see the system. Alright, you pick a vector from the row space, and then this is how A operates, and you project it on a vector B that is sitting in the column space. Right? Remember, B needs to be in the column space in order to have the solvable system. This is how it will look like. You have A times some vector xr, which is sitting in the row space. It gives you the outcome in terms of B, where B is sitting in the column space of A. This is what we mean by solvability of the system AXR equal to B, where XR is coming from, the row space. Well, you have, let's say, the set of solution to the homogeneous system Xn. Alright, Xn is sitting in the null space, right? When you solve Ax equal to 0, this is what you really get. Alright, so Axn equal to 0. Okay, so any vector sitting in the null space, if you operate, if A operates on that particular vector from the null space, it will project it to 0. Alright, so that means this vector solves Axn equal to 0. Now remember, our original vector x is a part of Rn, and as I mentioned earlier that everything in Rn can be rewritten as a linear combination of bases from here and bases from here. Okay, so our vector x could be a combination of these two. Alright, so our vector x, let's say x is xr plus xn. Alright, think about it, what it really does. Alright, this will solve our system Ax equal to B, where x is a combination of a vector coming from the row space and null space. Okay, this picture is called the big picture. as it represent the idea of this system Ax equal to b in terms of this nice subspaces which are orthogonal to each other. Alright, again a very simple and very nice way to represent it. You guys must have noticed that this is really the picture sitting on the front page of our textbook, right? It's an important thing, and that's why it's part of that first page. This is what we will be doing throughout the semester. Alright, so let me stop the video here. I'll show you some example of how to calculate orthogonal complement. Alright.